we'll continue our discussion with the next topic, scopes and closures. Scopes determine the accessibility of variables. The scope that we're going to be talking about is going to be related to just Node.js. The browsers, because they have this special global window objects, their scopes have other rule sets. Okay, so everything that we're talking about in this lecture is related to Node.js. In Node.js, there are three types of scope: global scope, function scope, and lexical scope, also called block scope. In Node.js, variables defined without a let, const, or var are considered global scope. So in this example, okay, we have a function which we call immediately, and then this function, when it's called, we use this variable global underscore variable, and we assign it the value 10, but because we don't have any of the keyword declarations, for instance, let, const, or var, this variable is defined to be global. So once a variable is defined to be global, it is accessible from anywhere inside of the program. Okay, so it can be used anywhere as long as that program exists. So this will break the notions of scope that you may have covered in your previous classes, in that normally if you declare a function itself, these variables should be scoped to that function. But because this variable itself was defined to be global, we can access it from anywhere as long as the program is still running. So this includes down here. So if we run this, okay, so we'll get the number 10. So this behavior typically we don't want. There's a specific reason why we scope our variables, so that we don't have to sort of do this cleanup behind us. In addition, having global variables, they cause a pollution of the namespace, which essentially means that no one else who is working with you on this project can use this variable. And in fact, if you have someone new join your team, if you're using global variables, then you have to sort of give them a list of all the global variables that they can't use, because global variables, they interfere with other files as well. So in fact, let's open up this second example. So this second example uses a Node.js require statement. So this is available only inside of Node.js. What it does is it imports on the second file, and so it jumps to a second file and it runs all the code inside of it. The Java equivalent would be the import statement. So we have this file open. Let's look at the code inside of it. Okay, so this file, all it does is it declares a global variable, which is set to be 12. And so if I run this file, line 2 is going to jump to this file. It's going to find a global variable, set it to be the value 12, and then it's going to come back from this file, at which point we'll print out. So let's run that. Okay, so this might actually seem like something that you want initially, where you sort of want this modularized behavior, where you can move some code into a separate file. But the problem with this is that, let's say that this variable was labeled I or something, okay? If you have like a large team of people, let's say 20 developers, then essentially you've just prevented everyone else from using this variable I. Okay, this is what we mean by namespace pollution, that anyone who's working on your project can no longer use this variable I. And there are much better ways to modularize your code. Okay, typically you would use the module.export syntax. So something like this. So you would say module.exports, and then you would assign it some data that you wanted. Okay, so it's not just restricted to objects. You can send back functions if you want, or let's have a function square. Const square equals x fat arrow times x, and then we can simplify this a bit and use that duplicating property of the object to set up the modules export. Okay, so essentially this sets up three variables: square, data1 and data2, and then we're putting them into the module.export. And so that itself gets caught. So when a require statement gets executed, that gets caught over here inside of file 2. Okay, and so from here, we can destructure it if we want. Okay, data1, data2, and square. Okay, so let's save both of these files and we'll run. Okay, so this is probably a more appropriate way if you want to modularize your code. In this scenario, essentially this behaves more like a function call where we're passing back some data from this file inside of the export variable, which then gets caught, and then we create local versions of that variable. So this is a much better way to do it than to use globals. Usually you can almost always avoid globals. You don't need globals for the most part, with maybe a handful of exceptions. If you're let's say working on the Node.js project or some other very specific to the JavaScript language as a project, maybe like a web browser or something. But beyond that, you should, as a application developer, you should avoid global variables as much as you can, because they cause problems when you try to scale. Okay, so the next type of scope is the function scope. In Node.js, variables declared using the var keyword have function scope. And these variables are scoped to the function in which they're defined. Okay, so in this first example, we have a function scope, which has a var declared keyword inside of it, var x is equal 10. And then if we call this function, okay, when this function returns, x should no longer be accessible because the variable x is scoped to the function scope. So once we're outside this function, we should not be able to access x. Okay, so if we run this, we'll see that we get an error. Okay, so we get an error, x is not defined, which makes sense. So this is called a top-level scope. So a variable is declared not inside any function using the var keyword. In fact, it also applies for let and const. Then it becomes a top-level scoped variable, in which case it is scoped to the file. Right, so this variable y is accessible anywhere inside of the file. The scopes nest on the way down. They don't nest on the way back up, but they nest on the way back inside of the function. So inside of the function scope, I am able to access this variable y. Okay, so in fact, let's do y++ so that we can see a change on each column. Okay, so 20 and 21. Okay, so this var declaration itself is scoped to the file. Okay, so what this means is if I use, let's say, let's not call this global, but we'll call this v1. And then inside of the other file, we will just say v1 is equal to 10. Okay, so this would make v1 a global variable. And if I run this, this will print out 10. Okay, but as soon as I add the keyword var in front of it, then this variable v1 is now scoped to the file, file2.js. And then when I run, let me add a second statement. Okay, so it should print out v1's value from inside of here, and then when we get back, we should get an error message when we try to print it from the demo file, because it is no longer in scope. Okay, so we get the message printed out, and it includes the value 10, and then we get an error over here because it's no longer in scope. Okay, so function scope itself, it's scoped to the function unless it's a top-level variable, in which case it's scoped to the file. Scope has a nesting property. If I declare a variable x on the top level, I can access that variable x throughout the file, including inside of functions. And this variable y would be accessible from inside of this scope function and including nested functions. And this function z, this variable z, is accessible from inside of the the nested function, but not outside of it. So once I leave this function, I can no longer access Z. And this is slightly different behavior than like a C-based language. Okay, so over here we can access X, Y, and Z. Now, if I declare my own version of X inside of here, okay, so this will not give me an error message. Okay, so even though I have two declarations for X, over here we have the declaration on top, and then a second one over here. If I have a declaration that is solely related to the function itself, essentially that version of X will be used while I'm inside of the scope. And then when I exit the scope, that value itself will be lost. So in fact, so if I just run this as is, I'll get an error because Z is scoped to just this function. And so I'm going to remove this Z over here, in which case I'm only printing out X and Y, and X should have the value 10, Y should have the value 20. This actually creates a new memory address, and when I'm referring to X inside the scope, it's going to be using that specific copy of X. Now if I don't have this var keyword, then I'm going to get very different behavior. Okay, and you can see that without that var keyword, this essentially replaces the original value of 10 with the string hello. So be careful with that. And finally, on this line, if you're outside of here, the only access that you can have is to variable X. Okay, so another weird property of the var keyword is that it has a property called hoisting. And what hoisting does is it essentially moves the declaration of a variable to the top of the statement. Let's just leave it with the var for now. So this will return back undefined. That is, line 1 will print out undefined. So if I run this, I'll get back undefined. But if I change it to let X is equal to 10, and I run this again, what I'll get is I'll get an error message. Okay, it'll say cannot access X before initialization. Okay, because X has not been initialized yet. So essentially, what is happening? Because in the previous case, X was also not initialized. Inside of JavaScript, it has this property called hoisting. If a var declaration is encountered, that var declaration is moved to the top of the function, and if it's a top-level scoped variable, that is, it's not inside of a function, then it's moved to the top of the file. So essentially, this is what is equivalent to be executed. And it's important to note that hoisting itself only moves the declaration. It doesn't move the assignment. Okay, so this is sort of syntactic sugar for what actually occurred. So we have var x, which allocates some memory on the stack for a variable x. Then we try to print it, in which case we get undefined. And then we assign the value 10, so it would have the value 10 afterwards. I can sort of show you that by removing this declaration entirely. If I remove this declaration entirely, okay, then what I'm going to get out of here, in fact, is going to be a bit strange. I'm going to get an error message. I'm not going to get undefined or anything. I'm just going to get an error message. Okay, it's going to say that X is not defined. So, but if I put in this var keyword, then I no longer get an error message. I'll just get undefined. Consider the following code. So we have something like if false. So this will never execute. But if I run this, then we still get the undefined statements because that var is hoisted up here. Okay, so function scope is also something that, in my opinion, can be completely avoided. My argument for why you should avoid it is not as strong as when I'm talking about global scope. Okay, global scope, you have severe issues with namespace pollution. The reason why I prefer lexical scope and block scope is because it's more intuitive to use, in that when you're using lexical scope or block scope variables, they're scoped to the curly braces. They don't have this weird hoisting property that you have to keep in the back of your mind. It's a slightly weaker argument. Okay, you can choose to use var if you are used to it, but I haven't personally encountered a situation where I needed to use var over using a letter const. Okay, so let's talk about the third type of scope. This is the one that I recommend that everyone use. It is part of the ES6 language, so the most recent version, the most recent major change inside of JavaScript. And that is block scope, also called lexical scope. So in Node.js, variables declared using either the let or the const keyword. So let, of course, is a regular variable, and const is a constant. You can't change it afterwards. Have this lexical scope. And these variables essentially are scoped to the set of curly braces in which they are defined. So it's literally the actual characters, the curly braces. So if I have some variables declared inside of here, then when I'm outside of here, they are no longer part of the scope. Okay, and these curly braces can be anything. They can be an if statement, they can be a for loop, they can be a switch statement. Alright, so inside of here, we declare a variable 5, and if I'm inside of the set of curly braces, then I can print out that variable, but as soon as I leave the set of curly braces, it is no longer in scope, and I will get an error message if I try to access it, which is what I expect. Okay, I want this error message because I'm trying to access something that was declared inside of this particular scope. Okay, so this scope is no longer restricted to just functions. With var, it's restricted to just functions, but with let in const, it's restricted to the set of curly braces in which it's defined under. Okay, so over here we have variables x and y. X uses var, and y uses let to define it. And then when we run this, and we do console after the loop, we should be able to access x because x has that hoisting property, so it gets moved to the top of, in this case, the file because it's a top-level variable. Whereas the let is scoped to the loop itself because it's defined inside the loop, and so we should not be able to access y. Okay, so we're able to access and print out the number 10, but we are not able to access y because it falls out of scope once it reaches the end of the curly braces. The same happens for a conditional statement. Okay, so we have the following. This also applies. And in fact, one of the interesting things in JavaScript is that when I said that it's actually tied to the curly braces, that's the case. This code actually is syntactically correct. These characters themselves are called the scope operators, and you are allowed to have code that looks like this. Now, I personally have only found myself needing this in sort of one very edge case, but it's not something that I've ever seen myself need in production. But this will also have that same effect in that variables declared with var are accessible, and then variables defined using letter const are not accessible. Okay, so again, 10 prints out, and then we get an error code when we try to do y, but this is syntactically it's fine. So the one special case for lexical scoped variables is the for loop. Specifically, the for loop with the declaration inside of the initialization phase. Okay, so the for loop that we know, it contains an initialization phase, a condition statement, and an increment. And the question that arises often is this declaration inside this for loop, is it scoped to the inside of the loop? That is this declaration inside of here, or is it outside of here? And so the first thing that you might think is that it would be outside, okay? Because if you make it inside, you're redeclaring that variable I over and over again. which resets its value. Okay, so the only way it could make sense is by making it outside. Okay, so we have let I equal 0, or in fact, we could just say let I, in fact. And then we have I equals 0, I is less than 10, I plus plus, print. So this is fine, except that if I try to print out I afterwards, if it actually is a direct translation of right before it declared the variable I, then I should be able to access it, which is not the case. That is, if I just do let I equal 0 and I run this, then in fact, outside of this loop, I can't access it. It'll give me an error message. It'll say I is not defined. It's not outside and it's not inside. So where would it actually be? And this is where I would use the scope operator to explain what is actually happening with the for loop. So syntactically, if it's outside, the declaration is outside of here, then that has a side effect in which it is accessible from outside the loop, and which is not actually something that I want. Usually if I'm declaring a variable I want it to be scoped to inside this loop, but I don't want that declaration to lose scope while it's in the duration of the loop. So syntactically, we can think about it as equivalent to the following. Okay, so this is, in fact, I don't need this I equals 0. This is probably closer to what is happening under the hood. So this is, if we see this for loop, this is closer to what's happening under the hood. And this is the only case that I can think of where I can use the scope operator to explain something, but we do have the syntactic sugar version over here. Okay, so what's happening? So essentially what I'm saying is that this and this are the same. Okay, so we have a set of scope operators, and essentially inside the scope operators I declare a variable I, which means that outside of this loop, or outside of this syntactic sugar for the loop, I cannot access I. But inside of here, okay, so while I'm inside of this loop, then I can use this shared version of I. I'm not doing a new declaration every time. So it's definitely on the outside of the loop, but there are these additional sort of hidden scope operators that ensures that I can't access variable I once this loop finishes, which is what I want. That is, I want the variable I scoped to this loop, but I do want it to increment it as we're working through. So that's essentially the only sort of case where I can see this scope operator being useful, and it's just to sort of explain the syntactic sugar for a for loop. Otherwise, I haven't personally encountered a scenario where I needed scope operators. Okay, so next let's talk about higher order functions. So higher order functions are functions that take in another function as either its input. And examples of that include like the array's map or filter function. It takes in another function as its input. And then in the case of the map, it applies some function to all the elements of that array. And in the example of filter, it throws away all elements that failed that test that the function performed on it. The other use case for higher order functions, okay, is so it doesn't have to be just one that takes in a function as its input. It can also be a function that returns a function as its output, and then those are the ones that we're going to be looking at today. So functions that return functions as its outputs. So you can think about like a function generator. Okay, so first we'll look at a simple example to explain how this works. So we have this function outer. Okay, outer declares two variables, b and unused. It has a input parameter a. Okay, and then it has a return statement over here that returns another function called inner. Okay, so it's returning back. So when I call outer, I'm going to get back a function as the result. Okay, so when I call outer, essentially this variable I gets assigned this function. Now this function I over here, this variable I, is actually a function. So if I give it a set of parentheses, that performs a function call. So I can call this variable I anything I want, in fact, but as soon as I use a set of parentheses over here, I'm calling the inner function. Okay, so I'm passing, in this case, the number 30 into the function inner. So that gets assigned to the variable C. Inside of this function, we declare a variable D, and then it returns A, B, C, and D. So A in this case would be associated with the outer variables 10. B would be this declared variable 20. C would be this input parameter 30. And D would be this variable 40. So as I'm expecting it to print out 10, 20, 30, 40. This over here is creating a new function, okay, that has some of the old variables sort of stored up. So let's try this one more time. Okay, so first we're calling outer on 50. So 50 gets assigned to A. B takes on its value of 20. And then we return back this function over here. So it's important to note that essentially every time I'm using this return statement with this function variable over here, this is creating a new function. Okay, so this is not a reference. This is putting a new function on the, well, it is a reference, it's putting a new function, but it's putting a new function on the heap. Okay, so specifically this second call to inner that we're doing is unrelated to the one previous. Okay, so this is a new variable B, a new variable A, and so on. Okay, so this is going to be 50, and then when I call inner on 60, okay, what's going to print out is going to be 50, 20, okay, because that's fixed, the B is fixed. C is going to have 60, and then D is going to have 40. So let's run this. Oh, J2 has already been declared. Okay, so this should be J1, that's why. There you go. Okay, so 50, 20, 60, and 40. So this is the first example of a closure. Okay, and so what a closure does is it preserves our access to variables that are no longer in scope. That is, after I call the function outer, and I return back to the top level scope, then I'm no longer inside of this variable, this function outer, and these variables, A, B, and unused, essentially, under normal conditions, I should not be able to access them because I'm no longer inside of that function scope. Now, the problem that occurs is that the function that it gives me back, this function inner, it uses those variables A, B, C, and D. Okay, so it uses those variables A, B, C, and D. So if I do like garbage collection on those variables A, B, C, and D, then all of a sudden this function that I return back becomes useless. So what a closure does is it'll say that, okay, if you have these higher order functions, a function that returns back a function, and that function needs access to some other variables, for instance, A and B in this case, then a closure will preserve your access, or this function's access, to variables A and B. Okay, so let me illustrate it. Okay, so inside of the outer function, we have, in fact, 4 variables defined. We have 3 of them are obvious, A, B, and unused. Okay, and then this this function over here also counts as a variable. Now, this inner function, okay, this inner function, in order to work, it needs access to A and B. It doesn't need access to unused. Okay, so in fact, that is a candidate for garbage collection. But essentially, because this inner function, the return statement over here, uses A, B, C, and D, because it uses A and B, essentially it's going to put a reference counter onto that memory address. And as long as the inner function remains in scope, then it will prevent variables A and B from being garbage collected. Okay, and this is essentially what a closure does. It is the inner function is preserving its access to A and B. So not all variables get preserved. Even if the inner function didn't use unused, and there was no other function that used this variable, then it would be a candidate for garbage collection because it's no longer used. Okay, it doesn't mean that it wasn't ever used. It just means that this specific calls to the inner function no longer doesn't need it. If you have like temporary variables or something, those are generally candidates for garbage collection. Even though these variables are preserved, in this case A and B are preserved, the only one who can access A and B is going to be the function inner. That is, from a programming perspective, when I come back over here to the top level code, I cannot access A directly. If I try to do console.log of A or something, that won't work. I'll get an error message because it's not in my scope. Okay, so I'll get an error message that A is not defined, but I know A is available to access from the inner function because it's being printed out over here. So even though it is part of memory, it's not something that when we return from this function we can access. And that includes if I try to use like a dot operation on the variable I or j. It's very difficult for me to prove to you that unused is not preserved. But there's actually a tool that the Chrome browser currently has. This is actually not inside of Firefox. It's only inside the Chrome browser from my research. And essentially, the Chrome browser has a very cool tool that lets us look at the scope of variables via a command called console.dir. So we've used console.log to print out information about variables. But there's a function called console.dir that its primary use was to print out all the properties of a variable. Okay, so for functions, that's not that useful in Node.js. Let me just run it once to see what we get. Yeah, so we just get like this function, and because it's a function, there's nothing really inside of it. Okay, but inside of the Chrome debugger, actually it gives us a little bit of additional information. So we still get this function inner, but it also gives us on the very bottom a scopes, and essentially this lets us look into the memory a bit. And if I look into this memory, it'll say that you have a global variable which contains all the global variables. This is just from the browser information, so like the browser will have a window variable, have a document variable, and so on. Okay, so like I said, globals are a bit messier on the browser level. Okay, but we are interested in this closure. And if we look at this closure over here, it'll say that okay, there's a closure that preserves. Okay, there's a closure called outer. Okay, there's a closure called outer that preserves access to the variable b. And the reason for that is because this variable x, which preserves the variable inner, essentially needs access to this variable b. What you will also see is unused is not preserved. Okay, because I don't use it inside of here. Now if I do use it, let's say, now the level of usage is very simple. That is, it can be something like an assignment statement or something. it can be just a call to it. So I'm just calling it. That, in fact, that would be the simplest, in fact, where I don't even do any changes to it. I just say, what's in the value of this variable, in fact, and then just continue on with the program. That is enough to essentially keep a closure around it. When I look at the scopes now, we'll preserve the variable unused. So garbage collection, in fact, with regard to closures is actually a undecidable problem. So this one is not that useful as a higher order function. It's definitely a constructed example. But let's look at a slightly more useful higher order function. Specifically, this one is called the not function. Like, the learning higher order functions is very difficult, and this is probably this is like the hello world of higher order functions, but it's still extremely difficult if you are not used to it. So the key thing to remember is that higher order functions, with regard to this class, is a function that returns back another function. Okay. Again, it could take a function as input, but we're more interested in the output. And in fact, this not function does both. So it takes a function as its input, but more importantly, the return value, the return statement of this not function is another function. Okay, so this is the syntax for another function. Okay, so let's look at what this function does. Okay, so first we have a keyword function, function name, and then a parameter. And this is just going to signal to us that this input is a function. Okay, so the input is a function. And then immediately we have a return statement. And again, because of today's class, we said that we're interested in functions that return other functions. This over here, okay, we can ignore the syntax for now, is going to be a function. Okay, so let's look at the syntax next. So essentially, this is an arrow function. And in fact, let's just ignore this for now, okay, to make it a little bit simpler. Okay, and so this is an arrow function. So here, this is the parentheses representing the parameters, which returns a negation of the func variable. Okay, so next let's look at these args variables. So this args variable is not a keyword. I can call it anything I want. I could call it r if I wanted to. It is not a keyword. Okay, so this is a REST operator, which essentially says convert, okay, this list of parameters. So this is the input parameters. So convert it into an array. And then we have the spread operator over here to convert it back into a list of parameters. So all this is doing is saying, take all the input parameters of this function. I don't know how many there are, okay, because this function may have 0 input parameters, it may have 1 input parameter, it may have 2 input parameters, it may have n input parameters, okay. Take all those input parameters from this new function and forward it to this func function. Okay, so essentially I'm creating a function that will take 0 or more parameters. Okay, so this is a new function that takes 0 or more parameters and then calls the func function passing in those parameters. So you can sort of see I'm forwarding essentially these parameters into this func function. And then if this function returns back true, I'm going to return back false. And if it returns back false, I'm going to return back true. Okay, so that's what this not function does. It creates a function that is the negation of the inputted function. Over here, we have a function isEven. Okay, so this is a very simple arrow function. X as the input, fat arrow, and then the condition is x mod 2 equals 0. If this is true, this will return back true. If it's false, it'll return back false. Then it's not even. Okay, so that is the isEven function. And in fact, we can quickly test it. Let's just use a browser. We still have this open, so I can use this. So isEven of 10 is true, isEven of 9 is false, isEven of 8 is true, and isEven of 7 is false. Okay, so so this looks fine. So now we're going to use that not function to essentially negate this function. So we take the definition of isEven, and we pass it in to the not function. Now this creates a new function that will call isEven. Any results that we get back, we negate that results. So it's important to note that this does not do a function call. This returns a function definition. Okay, so this function is not being called, well, the isEven function is not being called at all when I'm executing this not function. Okay, so there's no function call to isEven over here. This is returning back a function that will call isEven in the future. And let me just hide this for now. Okay, so is 41 odd? True. Is 42 odd? False. Now, there is actually a built-in function called number.isInteger. So the not function that we constructed can also work with built-in functions. Okay, in fact, it can essentially work with any function that, in this case, returns back true or false. That would be the sort of key restriction. So in this case, we're saying is 420.69 an integer, and then we're calling number.isInteger. So this will showcase the built-in function. And then we apply the not function to number.isInteger, which will give us back a new function saved to is not an integer. Okay, so is 420.69 an integer? False. Is 420.69 not an integer? True. Okay, so let's look at the next example. So we have this function isEven, and we have this function isOdd. What happens if I reset the definition of isEven under the hood? And in fact, what happens if I reset the function not to be undefined? That is, I'm erasing the values inside of here. Does this isOdd function still work? Okay, and if so, how does it work? Okay, and so the result may be a bit surprising, but it does still work. That is 41 odd? True. And is 42 odd? We get back false. Okay, but so let's look at what happens memory-wise. So the first thing that's defined, the first thing that we encounter, in fact, is this function declaration. And in fact, function declarations, as we've covered previously, are just variables. Okay, so we're going to create a new variable. We're going to create a new variable not. We're going to associate some memory to it. And then that's going to have some function definition associated with it, which is going to be this function over here. Okay, that's going to be the definition of the not function, in fact. So I'll put not over here, function not. Okay, so this is the function definition of not. The next thing we do is we define the variable isEven. Okay, so isEven, initially undefined, and then we assign it a value, which is a function. So we'll say that this is the function isEven. Okay, so this function is stored on the heap. And then we declare a new function, isOdd, which takes on some memory address. And then the next thing we need to do is we need to evaluate this function, not of isEven. Okay, so we call this function, not isEven. We pass in this memory address, okay, for the isEven function. And then this return statement is a new object. Okay, so this creates a new object. The same way that if we have an arrow function that returns back an object over here. So in this case, we have a return statement that returns back a function, okay, which is an object. So because this is a new object, we need to allocate new memory space to it, okay, which is over here, okay? And so this would be essentially this new unnamed function. So this new function itself will call the arguments parameter, which contains isEven. So that one becomes preserved by the closure. And in fact, I think that's the only one that's preserved. I don't think the not is preserved, which is fine because we don't really need it. So maybe in fact this one is not necessary. But isEven is preserved. So isEven is preserved. Reset this value to be undefined, and we reset this value to be undefined. The memory addresses in the heap are still allocated, okay? And then when the garbage collection process goes through them, this function for isOdd has a dependency on the isEven function. And the key thing is the isEven function. This one gets preserved because of it's represented as the args variable over here, and the closure itself prevents it from being garbage collected. So even if we lose our pointers to the isEven function over here, the isOdd function preserves our access to it. So finally, what are closures used for? So closures are used essentially in 3 places. We'll be using them in asynchronous programming, which we'll discuss next. But if we're just talking about top-down procedural code, then we can use them to hide private members. And we can also use them for counters. Okay, so this code may look slightly familiar right away. It looks very much like a class, but it's a function. Okay, this is function dog. And when we call a function dog and we supply the input parameter n, it creates a variable name, age, and inventory. It declares a couple of other functions, bark, birthday, pickup, and display information. And then it returns back an object that contains these functions, bark, birthday, and pickup. Okay, and looks like we can sort of use this as a pseudo class type behavior. In fact, this pattern is called the revealing module pattern. It's also sometimes called the function factory, or the object factory. And essentially what it does is it uses closures to preserve our access to specific variables, name, age, and inventory. But once we have an instance of, in this case, a dog, then we can no longer directly access those variables. So this code created 2 variables, Sparky and Fluffy, which essentially are objects that contain 3 different functions. Okay, bark, birthday, and pickup. So I'm able to call these functions like sparky.bark and sparky.birthday. And the interesting thing is that there are variables, name, age, and inventory, that are maintained. Okay, the closure maintains access to those variables, but I am not able to access them directly. So I cannot say sparky.name, or I can't say sparky.age. Okay, so we can sort of think about it as very similar to sort of private variables. And so this syntax is called the revealing module pattern. And the key component is the return statement. Essentially, we define our primitive, we define our instance variables for the specific class that we're trying to sort of simulate. We define the functions, okay, that we're going to be using. And then we return back an object that contains a list of publicly accessible functions. These have to be functions, in fact. You can't actually put these properties over here. And the reason why you can't put properties inside of here is because these properties, well, I think if it's like a array or something, you should be fine. But if you use a primitive type, like a name or an age, then you're not passing a reference, you're passing a value back. So you're creating a new name or age, and then when you try to use them, it might look correct initially, but you'll sort of see that you can't change those values, or any changes that you make don't persist. So if I later decide that I want to use if I return back a name property and I try to change it, then that name itself will not be, it won't persist. Okay, so so if you want to have the ability to change, for instance, name, age, or inventory, you do so via getters and setters. So you need a specific function that is returned back. Over here we have a private function, display information, that is not returned back. But this function is preserved because the function pickup calls it. So pickup preserves display information, and then display information is one of the functions that preserves the name and inventory. Okay, so there can in fact be multiple functions that sort of preserve that form a closure, and essentially as long as there's at least one function that utilizes one of these variables over here, that variable will be preserved by the closure. Okay, so we create two dogs, Sparky and Fluffy. We call Sparky.birthday, so that prints out Sparky is 1. We call Sparky.birthday again, it's 2. We call Fluffy.birthday, that's 1. So notice that essentially these age variables are essentially counters, and the counters themselves are independent between each instance because a new memory address is created for each one. Sparky picked up a bone, so that is line 27. And then Sparky has bone in their inventory, which is the display information function. Sparky picked up a chew toy, and then Sparky has bone and chew toy in their inventory. Okay, so we can see inventory is just an array, and we're essentially just printing out the contents of the array. And then if Fluffy picks up something like a food bowl, then her inventory is completely separate from Sparky's. So the other use case that's very common is just counters. And so let's just run this one first. So let's just start from down here. So over here, generate counter is a function that creates a new counter. So I create two counters. Maybe I need like two stopwatches or something. One called counter1 and one called counter2. If I call counter1.next, it'll print out a number, 1. And then if I call it again, it'll print out 2. And if I call it again, it'll print out 3. So if I call out next 3 times, I get 1, 2, and 3. And then I'm going to use counter2 to call next, which will give me 1, and then call it again to get 2. So we have two independent variables. And essentially, this is using the same revealing module pattern. So let's look at what's happening. Okay, so the first thing that I encounter is the declaration for generate counter. Okay, so that gets added to my call stack, and the definition of this function gets added to the heap. And then we have some address that gets assigned to our generate counter variable. Let counter 1. So we if you recall, that essentially is syntactic sugar for two statements. Let counter 1, and counter 1 is equal to generate counter. Okay, so initially it's undefined. And what happens is that we do the right-hand side first. So we essentially do a function call. Okay, and so because this is a function call, we create a new stack frame on the call stack, okay, to store any new variables. And so inside of the stack frame, we start running the code for the generate counter. Okay. So the first thing that happens is a index variable is declared and assigned the value 0. Okay. Then the function next is declared. And so we add that function next to our heap. And we set up the, well, maybe the pointer should go in the other direction. Okay. So that we call next, it goes to that heap address to run the function. And then, if you look very carefully, the return statement returns back a new object. So this creates a new object. Okay, so this line over here. So this line over here creates a new object, which has the next function inside of it. And so essentially this this object at 00cc is preserving our access to the next function. Okay, so it ensures that this function won't be garbage collected. And so that gets sent back over here to next. And then what happens finally is that this address is returned back to counter. So it gets the address 00cc. Okay, because that's what's returned back. So you can see counter 1 itself points to 00cc. And then this object, it has a next property that calls the function at address 00bb. And then this variable 00bb, which is this next function over here, it uses this variable index. Okay, so essentially this function, in order to function correctly, it needs access to this index variable. So through this series of sort of chaining together, this variable index is preserved. Okay, so essentially counter 1 has the value 00cc inside of it. And then 00cc has this variable next, which points to 00bb. And then 00bb itself uses index inside of it because that is the next function. So that will preserve our access to this index variable. So even when we return from this function, so essentially we're done with this function at this point once counter 1 has a value. Okay, so we are now outside of here. And essentially what this looks like memory-wise is the following. Specifically, when we return from this function call, that stack frame is popped off. Okay, and all the variables inside of it should be discarded. But because of this closure, because the function next forms a closure around index, okay, this function over here, 00bb, the next function, preserves our access to index. And what actually winds up happening is something, okay, so essentially we continue to have access to this index variable, or the next function for counter 1 has access to it. We can't access it directly. But then we continue the next step of calling generate counter again. And so that will create a new stack frame, which will have a new index associated with its own next function and its own return object. So we'll have the next function again and this return object. And all of these, because we see these function declarations over here, they are being declared on the heap, and they're creating new instances on the heap. And so when we return back, okay, again, we're going to have this index variable preserved, but this time for counter 2. So again, we have, when we return from this function again, we're going to pop off this stack, but this time index is going to be preserved again. And in fact, these identifiers are no longer important because, well, they're important for this function over here. But we can't access them by the identifier. Okay, in fact, there's 2 of them, so it wouldn't make sense. And in fact, I think this is an error. So let me fix this real fast. Okay, that should be 00EE because it's pointing to the object that points to this address for the function. But yeah, that essentially is how we have 2 index variables that are independent from each other. And essentially, every time we call next, over here we say counter 1.next 3 times. Essentially, counter 1 is pointing to 00cc. Okay, that is this address. The next, we call the next function, which is 00bb, which is this one. And then this calls function next on, this is the function definition next, which uses this variable. And so every time we call next inside of here, we do index plus plus, but it's referring to this version of index. So this is going to go 0 to 1 to 2 to 3. And then when I say counter2.next, that's going to be, let's use a different color blue. That's going to be 00EE, which is this address, which has a next property, which points to this function definition. And then this function definition is enclosed by this variable index. So when I say .next, this becomes 1, this becomes 2. Okay? And so that's essentially how closures work, and how essentially we're able to preserve access to variables on the stack and the heap even after that stack frame has been popped off.